for a person to intervene. Now, we also use the word autonomous in a different way to refer to sort of the level of complexity of the machine. And so we use words like automatic and automated and autonomous to refer to sort of a spectrum of complexity. This is, of course, challenging, as people will know here, because there's no clear place to draw the line between these types of systems. As one example, I've included example of thermostats up on top. So you've got sort of your old school mechanical thermostat that's very simple. It's just an automatic function. When it reaches a certain temperature, it'll go ahead and trigger either the heat or the air conditioning. You have your programmable thermostats that you might think of as maybe more automated. You put in a bunch of different temperatures, different times of day. And this is an example of the Nest learning thermostat that's built as a learning autonomous system. For those who are familiar with it, it's not, it's not super complicated, but it is a little bit more autonomous. And of course, one of the challenges here is that as things become more complicated, you may have a challenge of it being more difficult to predict specific actions in particular situations. I ran into this myself with a Nest a couple months ago, where I was on travel and I thought it was going to do a certain thing and it just wasn't. You wouldn't have really had that with a regular thermostat or a programmable one, where the operation is more transparent to the user. And then, of course, there's what task is actually being performed. It's sort of meaningless to talk about autonomy without relation to any particular task. Of course, something can be have a human in the loop for some tasks and could be fully autonomous in other ways. And this sort of goes without saying, but I'm going to say it anyways, that not all decisions are equal in terms of importance. Both a landmine and a toaster are very simple automatic systems, very simple mechanical functioning, but the decisions they're making or the tasks they're performing are quite different in terms of the level of risk and acceptability if it gets it wrong. Now, even within use of force decisions, there are many different types of decisions that are, or tasks that could be performed. And so it's worth, I'm not going to go through each of these in detail, but it's worth just pointing out there are different types of force that can be used. Lethal or non-lethal force, kinetic or non-kinetic force, destructive or non-destructive force. The target that you're going after is certainly different in different environments. There are both arguably moral distinctions here between, say, targeting something that has people in it, an aircraft, and has people on board, versus just a missile, something that's unoccupied. Certainly some people have argued there's a moral difference there. There are certainly very practical matters between targeting people, humans, where your decision about targeting may be based on something like human behavior, which is very difficult, even for humans, to make decisions about how do you determine whether a person is hostile or not in an environment based on their behavior, versus targeting things, where you may be targeting it based on the actual signature of the object itself, which is much easier to do in some cases. And even among things, some targets are more cooperative or easier. For example, enemy radars that are emitting in the electromagnetic spectrum are much easier to target than maybe vehicles or even something sometimes dual use, like maybe a ground vehicle, where distinguishing between a military and a civilian truck could be quite difficult. The environment matters quite a bit. Some environments are more cluttered than others. Things like the undersea environment are much simpler from a targeting perspective. If it's a giant metal object undersea, it is probably a military submarine, maybe one of yours, maybe an ally's, maybe one of yours, maybe an ally's, maybe one of theirs, but it's probably not a civilian object. Now, even within the engagement decision loop, there are many, many different types of tasks that are being performed. This particular task, selecting specific targets to engage, is the one that many people have focused on. This is the specific task that's been focused on by the US Department of Defense in their policy document, by Human Rights Watch in their papers, by the UN report by Christoph Heinz, the Special Rapporteur for Extrajudicial Killings, who wrote a report on this, by ICRAC in the UNCCW discussions, by the ICRC. This is where people have tended to focus. It's worth pointing out that there are other relevant tasks in terms of making decisions. Many of these other ones, and I'll talk about this in a minute, are already automated today. Okay, so how is autonomy used in weapons today? I'm going to walk through this decision, sort of selecting specific targets for engagement, or this task. And maybe decision is a little bit too anthropomorphic, but it's easy to sort of slip into that kind of language. So I talked about systems where a person is selecting a specific target, a person is in the loop on this decision. There are many, many military systems in use today. Among them, and really chief among them, is homing munitions that are intended to go after a particular target that a person is sort of aiming the homing munition at. Now, the weapon itself may be very autonomous in the sense of a person being out of the loop in terms of being able to recall it. So many homing munitions, once released, they cannot be recalled. Some of them actually lock onto the target after launch. So they're basically aimed at a target. And then they get to a certain point in space, turn their seeker on, and the intent is that what is inside the seeker's field of view is the target that the person has intended. These are very, I guess, commonly used by many nations around the world, have been since World War II, when torpedoes were first introduced. You have unmanned aircraft today with things like GPS-guided bombs. There's certainly a certain level of autonomy in a GPS-guided bomb. The CRAM system, the Counter Rocket Artillery Motor System, is a US system that is used to shoot down rockets and mortars that are coming into US bases overseas. It is often referred to as a supervised autonomous system. A person is out of the loop. That's not actually true. A person is in the loop. A person actually pushes a button for every single CRAM engagement. But there is still a high degree of automation within the system. Centrifuge weapon is a US air-to-ground submunition that releases a number of smaller submunitions that individually target tanks. But the weapon as a whole is launched by a person at a particular group of enemy vehicles. And then you have things like intercontinental ballistic missiles. If you have, say, a merged ICBM that has multiple independently targeted warheads, you have a system that, once launched, flies through space, releases multiple warheads that then individually go after targets. But of course, those targets have been programmed by a person ahead of time. So the person is selecting what targets to go after. Now, you do have some examples in use today by a number of countries of systems that have a person on the loop, where the machine is actually selecting the particular targets that are being engaged. A person can intervene. Now, a person may or may not have time to intervene before any particular engagement is actually complete. In fact, in many cases, if the machine goes awry, if it malfunctions in some way, the person may not realize it's malfunctioning until an engagement has already occurred that is bad in some way. Maybe it's shot a civilian target or a military-friendly target. But a person can ultimately intervene to shut the system off. Some examples are the US Aegis ship defense system, the Patriot air and missile defense system. These are both US systems. And then active protection systems for ground vehicles, which are widely used by many countries around the world. Israel, Russia, South Africa, Germany, France, a number of other countries. These are basically protection systems that are on ground vehicles to shoot down incoming RPGs or guided missiles that might come at a tank. They shoot out kinetic interceptors that hit to kill to blow up the missile before they hit the tank. The time of engagement is such that these have to be automatic in order for them to work. If you try to put a person in the loop, it would be just physically impossible. But again, in all of these, a person can intervene. It's also worth pointing out in all of these are used to defend manned installations or vehicles, and people are physically co-located with them. So none of these are actually unmanned systems. So even if the system were to go completely awry, let's say there was just a software malfunction and it wasn't responding to your commands to turn it off, there is some mechanism by which a person could ultimately just physically disable the system, unplug the power source or something like that. Now, there are some human out-of-the-loop weapons. One example, a non-lethal anti-materiel system, is the US MALD-J. It jams enemy radars. It's sort of an odd thing in that it's not a missile, it's not a UAV. It's sort of like an air-launched cruise missile which launched from a US aircraft, and then it flies through enemy airspace, and it jams enemy radars. I don't want to overstate the level of autonomy in this, but it is a little bit more autonomous than other things. It's fair to say that it is selecting its own targets. But again, it's not using any kind of lethal force, and it's just targeting radars. There are a very small number of lethal offensive systems that are in use today. They're not particularly common. Two notable examples. One is the Israeli Harpy system. It's owned by a handful of countries. It basically is launched over an area, roughly maybe a couple hundred square kilometers, flies a search pattern looking for enemy radars. When it finds an enemy radar, it sort of kamikazes into it and blows up the radar. In that sense, it's more autonomous than some of these other weapons here, say a homing munition, because the person launching it may not know what particular target it's going after. It's simply flying into an area. The person knows that any enemy radars within this relatively large box will be targeted. There are a handful of US systems in the past that existed this way that are no longer in the United States' inventory. The Tomahawk anti-ship missile was one the US had in the 70s and 80s that basically operated this way against Soviet ships. It was launched, it would have been launched if it was used, over the horizon to search for Soviet ships based on the radars and then target them. It's no longer in the US inventory. Something else that's often mentioned is the low-cost autonomous attack system, the LOCAS. This was a developmental system by the United States in the 90s that was intended to go after ground vehicles like tanks. Again, it would fly over a wide area, find targets, and blow them up. It basically worked in testing, but there was a lack of comfort on the part of the US Air Force with delegating that level of decision-making, if you will, to an autonomous system, and so the program was ultimately canceled. The current version of it that is being touted by the developer, the US defense company building it, boasts a human in the loop for the current model. And the other sort of example in existence today that's probably worth mentioning is encapsulated torpedo mines. Now, mines are generally excluded from discussions about autonomous weapons for fairly good reasons. Mines are very simple. We understand how they work. They've been used for a long time. They're placed by a person in a particular spot on the ground. Obviously, the person's not involved after they're placed. They'll blow up when they meet whatever the target is. But the freedom of the mine is fairly constrained. Encapsulated torpedo mines work a little bit differently. Basically, what happens is when the passing ship comes by, the mine opens up and it releases a torpedo, which then homes in on a nearby ship. So depending on how you wanted to define the term, you could argue that an encapsulated torpedo mine is in fact choosing its own targets. Again, the United States used something called the Mark 60 Captor for a number of years. It's currently out of service. And Russia and China currently have encapsulated torpedo mines in their inventory. So there are a handful of examples of weapons of this type, lethal, human out-of-the-loop weapons that select targets on their own. They're very simple from the perspective of complexity. They're certainly not involved in any kind of human-level reasoning or learning, but there are a handful that do exist today. But it's not very common. So now I want to talk about the US policy on weapons, and particularly sort of what motivated the United States to do this. The policy is encapsulated in DoD Directive 3000.09, which was released in November of 2012. It's really the first sort of detailed policy by any nation, and it's still the case so far, that really covers how to think about autonomy and what's appropriate and what's not for future weapons. It covers not just unmanned things, not just what you would think of as robots, but also an autonomous weapon on a manned platform, if you were to build such a thing. It also covers things like wide area guided munitions that might be searching and destroying targets on their own, like the Harpy. Does not cover mines, does not cover cyber weapons, or things that are actually manually guided. Now, the purpose stated in this policy is to establish guidelines to minimize the probability and consequences of failures that could lead to unintended engagements. Just want to unpack this statement for a minute. The bad thing that the policy basically is intending to stop is an unintended engagement, which is defined on a paraphrase, but you could look at the actual definitions of the document, as basically something being blown up that the commander did not intend, or collateral damage that is in excess of what the commander envisioned was possible when they used the system. So basically blowing up the wrong thing. I think it's very clear. I want to make a point right here, the statement about minimizing the probability and consequences. This policy document assumes that 100% confidence is impossible. Accidents happen, people make mistakes. The objective is not to make something that is 100% fail-safe and can never fail. It's to minimize the likelihood of failures happening, and then if they occur, what the consequences of those failures could be. It is relatively conservative with respect to predicting future technology. And as I get to sort of what it does, you'll kind of see this. It builds basically a framework for going forward, but it does not say, I want to be very clear, sort of, if we look 20 years from now, this is the end-all be-all of what the sort of rules should be for how we think about autonomy in weapons. And there's probably some room for growth. So, let's talk a little bit about sort of why the United States did this. It was self-generated. The process that led to this document being published in the fall of 2012 was about a 3-year process internally. It was driven by a desire for guidance inside the United States military. At the time, I was working in the policy office in the Office of the Secretary of Defense, and we had people within the various branches of the military, and the Army and the Air Force, asking questions about, look, we're building these unmanned systems. Over time, they will have more autonomous features. How autonomous should they be? What are the rules? We know that at some point in time, especially when it comes to use of force, there are some really tricky policy and legal and ethical and moral issues. We need some guidance here. And so this was ultimately intended to give that kind of guidance. It was not driven by any particular system. It's not like there was something that someone in particular was building that they said, we want to be able to build this. It was driven more by an understanding that, that the technology is moving relatively rapidly in this area. And like I said, this was basically about a 3-year internal review process. So I want to talk about a concept that is embodied within the document. It's never really explicitly stated, but it was something that we thought about inside the working group, and many of these concepts are sort of encapsulated in different aspects of the directive. And that's just a notion of sort of appropriate autonomy, which is when we had worked on this issue and we sort of looked at all the different factors, we sort of settled on this concept that we want autonomy to be appropriate in the future. There's certainly many types of autonomy that you could envision that would be inappropriate or bad or not a good idea. And we came up with sort of 4 key concepts. One is that it has to be capable of accomplishing a military mission. And in some instances, this is going to include a desire for speed, such as in the case of defensive systems that are defending against incoming rockets or missiles that are attacking you. It's also, you're going to need to be able to operate in areas where your communications environment is degraded or jammed, or maybe you have no communications. So that's sort of one of the realities that we were looking at. A big issue is that you need to be robust against failures, but also an enemy trying to hack your system. Cyber warfare is an emerging area. It's not unique to robotic systems. Robotic systems introduce new levels of risk, and that if someone were to be able to take control, you don't have a person physically there who may be able to somehow shut the system off. So that was something we were very concerned about. We wanted to ensure that appropriate decisions are reserved for humans from both the perspective of legal accountability, public acceptability, and then military operational best practices. This is admittedly a rather squishy concept. What is appropriate? There's lots, I think you could have a whole lot of debate and discussion about that. We didn't choose to define what that means. The directive really lays out a series of parameters and questions and issues that people need to look at. And what we basically set up in the directive, and I'll talk about this in a minute, was a process for people to look through these issues as new things are developed. And the assumption that we made was that essentially if we forced people to ask these questions, that we could trust future humans to be able to make intelligent decisions and may come to reasonable judgments, so long as they were really forced to confront these issues. And then we took as a given, but I want to state it very clearly, that the weapon system was being used in a manner compliant with the laws of war. Discrimination and proportionality are 2 components of that. There are others as well, but these are the 2 big ones. The United States does a legal weapons review for every single weapon that is developed. So we didn't need a new policy to ensure this, but this is a component of appropriate autonomy. Okay, so with respect to these types of weapons that I described earlier, I want to explain now what the US policy says. What it basically says is for these three buckets, if you will, of weapon systems, they are okay to go build them. So if there's a human in the loop on selecting specific targets for use of force, go forth and do. That's very commonly been used. There are some general guidelines in the document about making sure that the person is making an informed decision about what targets to engage. But this is something that we have lots of experience with. The person's making a decision, not really any new issues here. With respect to human on-the-loop autonomy, where the machine is making the decision but a person can intervene, the directive allows those weapons, but they are very narrowly scoped for the use of lethal force. So if it is something that is being used for defense, for humans, for fixed installations, or for onboard defensive vehicles, then that's acceptable. If it's being used to defend against sort of time-critical saturation attacks, where speed is very important. But this is in the directive. It's a very narrow exception, quite frankly. And it also mandates that the system itself must either be physically on board a manned vehicle, or if it's for an installation, it must be for fixed static defense. So if you were to build, say, a roving air or ground robot that was defensive in nature, but it was sort of roaming on its own, it was an unmanned vehicle, that would fall outside of this exception. And I'll explain what that means here in a second. And then it allows human out-of-the-loop autonomy, where the machine selects targets on its own without a person being able to intervene for non-lethal, anti-materiel, non-kinetic weapons. So basically jamming, or maybe like an EMP pulse weapon, or a high-powered microwave that is targeting a physical object. And that would not be lethal to people. Now, the directive says is anything else outside of these three buckets, anything else that you could envision using autonomy, you could do basic research, but if you want to move into what the Department of Defense calls formal development, which is basically a stage where you start to spend a lot of money, which is kind of the main trigger, then you need to move through a very high-level review process that's quite involved before taking that step. And I'm going to explain kind of what that means in a second. So what does this mean for lethal, fully autonomous weapons in the future? Now, the US policy does not explicitly prohibit them, but outside of these very narrow exceptions that I explained, there are very severe restrictions. The review process that I mentioned is actually a two-stage process. The first stage happens before formal development. So as you move through the development process, when you reach the stage where you basically start to spend a lot of money, you have to go through this process. Even if you pass that review, again, before the weapon system is actually fielded, you need to go through another review. And the purpose of that really is to say, the formal development review process would basically say, look, if you're going to build this and it's acceptable, these are the parameters it needs to meet. The fielding stage, after you've done all the testing and everything else, is basically made to make sure that you now can do what you said you were going to be able to do with the weapon. That it hasn't changed somewhere along the way in a way that's really meaningful. Now, in order to pass this review, you need basically agreement from three very senior officials within the Department of Defense, the chairman of the Joint Chiefs, so the most senior US military official, and then the two most senior civilian officials inside the Pentagon for acquisitions and for policy. So the Undersecretary for Acquisitions and the Undersecretary for Policy. So you have sort of three main lenses through which you're reviewing a weapon system. The military lens, the acquisitions lens, and then the policy lens in terms of acceptability. Okay, so what are these actual criteria for this review process? In the document themselves, it's quite lengthy. It's several pages. I'm not going to go through all of them right here. You can take a look at it. It's on the US Department of Defense website. You could Google it and find it. But these are some of the highlights. Talks about appropriate levels of human judgment. It talks at length about safeties, anti-tampering mechanisms, so making sure someone can't sort of go up to your robot and somehow take control of it in some way. Information assurance against cyber hacking. verification and validation and test and evaluation within the process to make sure that it's going to function as you think it's going to function, particularly in real-world environments where you may have unexpected circumstances coming up, where you may have people trying to trick your system or spoof it or hack it in some way. It talks at length about training for operators to make sure that they actually understand how the system is going to function. So if you build the best system in the world and the people actually using it don't understand its capabilities and its limitations and where it will fall short and fail, it's not going to work very well. You need to think about the human component as well. And then, of course, a legal review is part of this. That is specific to the review process for those things that I talked about sort of in the red. In addition, there are some general requirements inside the DoD policy for any weapon system, including a semi-autonomous one. Similarly, there are issues about safeties and anti-tamper mechanisms, verification and validation. Human-machine interfaces are very important, that the person can understand how the system is functioning, so that a person is making basically an informed decision. And then there are requirements for sort of robustness to minimize failures and loss of control. And this is really, I think, a very key one from a robotics perspective, this idea of making sure that it's going to function as you expect it's going to do in realistic real-world environments outside of the laboratory and against adversaries that are going to try to thwart or trick the system in some way. Okay, so what does this mean for some of these broader discussions about lethal autonomous weapons? Many of the arguments against them hinge on this idea that they could not generally comply with the laws of war. Now, that may or may not be the case. I would argue that there are certainly things that you could build today, like the Harpy, that meet the definition of an autonomous weapon, that are selecting and engaging targets on their own, that could be used in a manner that are lawful and compliant with the laws of war. The Harpy does not strike me, at least, as an inherently illegal weapon. You could certainly envision things in the future that would be unlawful. It's hard to imagine them. But it's not clear to me that this is even the right question to be asking. It seems to me that the real issue is, if you could build autonomous weapons, would they be safe? How would we ensure that they're going to operate like we think we're going to operate in real-world environments? How could we ensure that we've done enough test and evaluation to know that there's not going to be some hidden bug in the system itself, or that there's not going to be some way that maybe we didn't anticipate, maybe the developers did not anticipate, where the person can trick the system into doing something wrong? And when failures occur, how do you ensure that it fails in a safe manner when a person is out of the loop? The human operates as an inherent level of fail-safe if a person's in the loop. If the system fails, the person can intervene in some way. If you take that away, what do you lose from a safety and reliability perspective? To me, this is really about robustness, reliability. It's ultimately about trust over these systems in environments that are very, very challenging and with decisions or tasks that are very consequential, with life or death decisions. This, to me, is an interesting discussion from the perspective of roboticists, because better than anyone, roboticists understand the challenges in building reliable systems that function in uncontrolled environments. So that's it for me. I think we've got someone else coming up. Thanks for your time. And then I don't know if we'll do questions now or we'll just do it in the panel at the end. Okay. We have time for, I guess, one or two questions.
I'll take questions. Yeah.
So on this last point, and I'll use the Google car as a stand-in. For sure, Google cars will be safer than humans. Humans are not great drivers, and Google cars will be better. What's also almost certainly going to be the case is that a Google car will kill someone somewhere along the way that a human would not have. That is, Google car will occasionally make a mistake that a human might not have made, but still overall the Google car is generally safer because all these mistakes humans would have made, the Google car won't. So it would seem to me your weapon systems should be subject to the same kind of conversation, right? I mean, you might be way better at making decisions most of the time than a human would be, but occasionally will make a mistake that a human wouldn't make. The current framework here might preclude you from using such a system, because actually, you can't totally trust it, even though it's better than humans, who you also, by the way, can't totally trust. And I'm just wondering if there's been conversation about that trade-off.
Sure. So a couple of things about that. One, as I think most people understand, the environment that Google is operating their cars in Silicon Valley is one where they've been able to map the environment to a high degree of precision. And so they understand the environment quite well. They're not, so I think that's one of the challenges about this situation, which is different in that you may not understand the environment, and there's a level of someone trying to attack your system that you're probably not going to face with the Google car. You may get to a situation in the future where we say have pedestrians blithely walking in front of autonomous cars because they know they're going to stop. There's probably some moral hazard there, and we may see that. But this is a little bit more challenging. But to your basic point, I think there are kind of two ways of looking at this. One is this idea that if autonomous weapons are better than humans, then we should use them. That's again where I think it's worth distinguishing between autonomy in the sense of more complexity versus the sort of the human-machine relationship. So if we could build more autonomous features or more automated features into weapons that could say allow them to identify and flag for humans maybe when the civilians have moved into the target area, that's great, and there's really no downside to that. I think the more basic issue is when you start to take a person out of the loop entirely, what is the risk associated with that? I think there are reasons why you might want to do that. If you can't have communications in that environment because maybe it's underwater, so communications are challenging, or you're going into a place where the enemy is jamming your communications. What is, I think, different is that it's not, to me, I don't look at the issue of just a single system malfunctioning. If that's what you were limited to, I think it's probably pretty straightforward. Humans make mistakes. Fratricide events are unfortunate in warfare, but they do happen, and they will continue to happen so long as people fight wars. What is different is that when fratricides happen and people make those mistakes, they are generally isolated in space and time. So if a pilot misunderstands sort of the target and drops a bomb on the wrong people and friendlies, that's going to happen in that one place. What is conceivable with autonomous weapons is that you could have massive incidents across the entire battle space. So if there is a fundamental flaw in targeting and the system targets friendlies or targets civilians because of some failure mode, you would not have that in just one system, you may have them across all of them. Now, if a person is in the loop, if it's a homing munition, then ideally people could step in and realize that failure relatively early on. There's sort of actually a real-world example of this. In 2003, the US Patriot system for a variety of reasons, had some incidents where it started to engage friendly aircraft. Shot down 2 friendly aircraft in 2 different instances. After the first instance, the way in which the system was used was much more tightly restricted. There was still another fratricide, and after that, human control tamped down even more. That's because people were able to sort of control the system, they were on the loop. You can imagine where if a person was out of the loop entirely, you launched a whole bunch of autonomous vehicles that were roaming around the battle space, and that failure occurred, you could have a significant amount of